Welcome to today's deep dive. We are really thrilled to have you with us.
Yeah, thanks for tuning in.
So I want you to start by, well, imagining something for a second. Imagine spending like 3 months building this incredible, perfectly intricate, custom piece of furniture out in your garage,
Oh boy.
right? You have it perfectly leveled on the concrete. The hinges are calibrated to the absolute millimeter. It looks just beautiful.
Sounds like a lot of work.
Oh, totally. But then, the big day comes, you carry this masterpiece inside to your living room. And suddenly, because the living room floor has this tiny, almost imperceptible slant, and the ambient humidity in the house is just a little different than the garage.
The doors won't open.
Exactly. The drawers get stuck. The whole thing essentially just, well, stops working entirely.
Yeah, because the environment changed. I mean, all that brilliant craftsmanship was completely dependent on the exact specific conditions of your garage.
Right. And in the physical world, that is frustrating. But in the world of software development, that exact scenario used to be a daily, multi-million-dollar nightmare.
Oh, absolutely.
And that actually brings us to our source material for today. We are looking at a stack of official documentation from Docker, specifically their Get Started, what is Docker, and what is a container guides.
Yeah, and these documents are crucial because they don't just, explain a piece of software. They document a fundamental shift in how the modern digital world actually operates behind the scenes.
Yeah, it's wild. So our mission today for you, the listener, is to really cut through all the dense, intimidating technical jargon.
Definitely a lot of jargon in this space.
So much. But whether you are like a curious learner who just wants to understand how the apps on your phone are served to you, or someone prepping to manage a massive cloud deployment, or just a developer tired of software dependency headaches.
We've all been there.
Right. We are going to build a beginner-friendly understanding of what containers actually are, how these things called images work, and why Docker has just fundamentally changed the tech industry. Okay, let's unpack this by looking at that custom furniture problem a little closer.
Yeah, let's do it.
In the tech world, they call it the works on my machine problem.
That phrase alone just gives developers anxiety. The documentation asks you to imagine you're building a modern web application. And to really understand the complexity here, we need to break down the pieces.
Right.
A typical app isn't just, one single file. It usually has a front end like React, a back-end API written in Python, and a database like PostgreSQL to store information.
Okay, let's translate that for anyone who doesn't write code every day. Think of your software application like a restaurant.
I like that.
Yeah, so React is the front end. It is the menu, the dining room, the tables, basically the things the user actually sees and interacts with.
Makes sense.
And Python is your waiter and your logic.
Right.
It's taking the orders from the dining room and carrying them to the back. And then the PostgreSQL database is your kitchen and pantry. It stores all the ingredients and raw data.
That is a really great way to visualize it. Now, to build that restaurant on your local laptop, you have to install the specific tools for the dining room, the specific tools for the waiters, and the specific shelving for the pantry.
Right, it's a lot of setup.
Yeah, you install Node.js for React, you install Python, and you install the PostgreSQL software, all on your own machine.
Which sounds totally fine until you have to actually share it with someone else.
Exactly, and that is where the nightmare begins. How do you make absolutely sure that the specific version of Python you are using is the exact same version your colleagues are using?
Yeah.
Or the same version the automated testing servers use? Or, honestly, most importantly, the exact version running on the final production server that your customers actually interact with?
And let's raise the stakes even more. Say you have another project on your computer, like an older application for a completely different client, and it requires an entirely different, much older version of Python. Yeah, now you have conflicting versions, basically, fighting each other on the same machine. You try to upgrade the waiter for one restaurant, and you accidentally fire the waiter for the other restaurant.
And boom, the app crashes. It is what developers affectionately call dependency hell. The whole system is just incredibly fragile. And this is the massive headache that Docker was designed to cure.
Thank goodness.
What's fascinating here is the core philosophy Docker uses to solve this. It completely separates the application from the infrastructure. Instead of installing all those languages and databases directly onto your computer's hard drive, you use a container.
Ah, the container. Basically the hero of our story today. According to the sources, a container is a loosely isolated environment that holds absolutely everything it needs to function.
Right, everything. The code, the runtime, the system tools, the system libraries, the settings. You essentially bundle the dining room, the waiter, and the kitchen into one sealed package.
Okay, so I am picturing a container like a highly advanced, perfectly packed lunchbox.
A lunchbox.
Yeah, hear me out. If you bring a regular brown bag lunch to work, you still have to rely on the office cafeteria, right?
True.
You need their microwave to heat it up. You need to grab a plastic fork from their drawer. Maybe you need to use their ketchup packets. If the cafeteria microwave is broken or they are out of forks, your lunch is essentially ruined.
Because your dependencies are not met by the host environment.
Exactly. But a Docker container is like this futuristic, self-heating lunchbox that already has a fork and condiment packets built right into the lid.
Oh, I see where you're going.
Yeah. It has zero reliance on the outside environment. You can eat it at the office, you can eat it in a park, you can eat it on an airplane, and the experience is guaranteed to be exactly the same because absolutely everything you need is securely locked inside that box.
That's a spot-on analogy.
Yeah.
Because they run in isolation, they simply do not care what else is installed on your host machine.
Right.
They don't interfere with each other at all.
Yeah.
You could run a container needing Python 2 and another needing Python 3 side by side, completely independently. Deleting one lunchbox has absolutely zero effect on the other lunchbox sitting right next to it.
Now, wait a second. I am trying to wrap my head around an isolated environment that runs an application. Isn't that just a virtual machine? Like, are we just talking about mini VMs here?
You know, that was probably the most common misconception. And really understanding the difference is crucial to understanding why Docker took over the world.
Okay, lay it on me.
So a virtual machine, or VM, includes an entire full-blown operating system.
Meaning it brings its own whole Windows or Linux setup.
Exactly. To run a VM, your computer's hardware has to run a piece of software called a hypervisor. And that hypervisor carves out a hard chunk of your physical RAM in your hard drive.
Okay.
Then it boots up an entirely separate guest operating system inside that chunk. It has its own kernel, its own hardware drivers, its own background programs, everything.
So if I am understanding this, a virtual machine is like building a completely separate standalone house for every single guest.
Yes.
Each house has to have its own poured concrete foundation, its own dedicated plumbing system, its own electrical grid, even if the guest is only going to sleep there for one single night.
That is incredibly heavy, and it creates a massive amount of overhead. I mean, you are allocating gigabytes of memory just to run redundant operating systems, simply to isolate one small Python application.
Wow, then a container would be more like an apartment building.
How so?
Like everyone has their own secure locked unit, their own isolated space, but they all share the main plumbing and the concrete foundation of the single building.
Yes, that captures the architecture perfectly. Docker is written in the Go programming language, and it cleverly utilizes specific features of the Linux kernel to create that apartment-style isolation without all the bloat.
The sources mention a technology called namespaces. How does a namespace actually work to isolate an app?
Think of namespaces like putting blinders on a horse.
Yeah.
The containerized application is the horse. The Linux kernel uses a namespace to put blinders on it, so the application can only see its own files, its own network ports, and its own processes.
Oh, wow.
Yeah, it literally does not know the rest of the computer exists. It thinks it is the only program running on the entire machine.
So it feels like it's in a private house, but it's really just wearing blinders inside the shared apartment building.
Exactly. And because it doesn't bring its own operating system and just shares the host's kernel, containers are incredibly lightweight. We're talking taking up megabytes instead of gigabytes. They start in milliseconds instead of minutes.
We should probably add a crucial nuance here because the documentation is very careful to point out that virtual machines and containers are not sworn enemies. Like, we aren't throwing VMs in the trash.
Oh, definitely not. In the real world, especially in cloud environments, they are actually used together to maximize efficiency.
Right, because when a company rents server space from Amazon or Google, the actual physical hardware they are renting is usually provisioned as a giant virtual machine. But instead of installing one application on that big, heavy VM, they install a container runtime on it and then run dozens or hundreds of lightweight containers on top of that single VM.
It's how you extract maximum density out of your infrastructure. Get the best of both worlds.
Okay, well, I am completely sold on the lunchbox concept. The isolation makes perfect sense to me. But if I want to give this exact same lunchbox to 500 different employees across the country, I am definitely not packing them by hand, one by one.
No, you definitely wouldn't want to do that.
So how do developers actually mass produce these things?
Well, to run a container, you first need a blueprint. In Docker terminology, that blueprint is called a Docker image.
An image.
Got it, yeah. If the container is the runnable instance, like the actual lunchbox doing the work, the image is the read-only template that contains the specific instructions for packing it.
And developers build this template using a file with a very simple syntax called a Docker file, right? You basically literally just write down the steps, like start with an operating system base, copy my restaurant's menu into it, install the waiter tools, and open the front door.
Exactly. But here's where it gets really interesting. It is how Docker handles those instructions under the hood. The documentation explains that every single command you write in a Docker file creates what is called a layer.
Ah, the magic of layers. This absolutely blew my mind when I read it. Break down how a layer actually functions for us.
Sure, think of layers like those transparent plastic sheets used on old-school overhead projectors.
Oh, yeah, from school.
Right. You lay down the first sheet, which might just be a bare-bones Linux environment like Ubuntu. That is your base layer.
Right.
Then you lay a second transparent sheet on top of it, which installs a web server, maybe something like Apache or Jinx. Then a third sheet goes on top, which contains your specific Python code.
So they just stack up.
Exactly. And when you look down from the top through all the sheets, you see the complete unified picture.
And the absolute brilliance of this is what happens when you make a change, right?
Yeah.
Say I find a typo in my Python code. Without layers, I'd have to repackage the entire operating system, the entire web server, and the code into one massive file and basically force my team to download a 2 GB update over the network.
Which takes forever.
Yeah.
But Docker is smart. It knows the Ubuntu layer hasn't changed. It knows the web server layer hasn't changed. So when you rebuild the image, it only creates a new transparent sheet for your modified code layer.
So I am only sending a few kilobytes of updated data over the network instead of gigabytes.
Exactly.
That perfectly explains why Docker images are so incredibly fast to download and share through registries like Docker Hub. Oh wait, I have to play devil's advocate for a second here.
Go ahead.
The sources explicitly state that a Docker image is a read-only template. It is locked.
Right. It's immutable.
If it is read-only, how does a running container actually do anything useful? I mean, applications need to write log files, they need to save user data, they need to modify things. How can an app function if its template cannot be altered?
That is a great question, and it brings us to the exact sequence of events that happens when you type the command docker run in your terminal. Docker does not just blindly turn on the read-only template, it constructs a dynamic environment around it.
Okay, walk us through those milliseconds. What is actually happening?
Let's say you don't have the image on your computer yet. First, Docker reaches out to a registry, which is the central library of images, and pulls those read-only layers down to your machine.
Okay, it stacks up the transparent sheets.
Right. Then it creates a new container instance. And to solve your read-only problem, Docker automatically allocates a final invisible layer right on top of the stack. This is the read-write file system layer.
Ah, so it's like a temporary scratch pad.
Exactly. The original image remains pristine and completely untouched underneath, but the running container uses this scratch pad on top to create, modify, or delete files. It can write its logs there, save temporary data, and basically do whatever it needs to do.
And Docker is also handling the networking during this split second too, right?
Yep, it creates a network interface, connects the container to a virtual network on your computer, assigns it an internal IP address, and sets it up so it can talk to the internet using your host machine's Wi-Fi.
That is crazy fast.
And only after all of that architecture is in place does it actually start executing your application code.
It is wild that all of that orchestration happens in literally the blink of an eye, which naturally leads us to wonder how this is all managed. Because typing Docker run feels like casting a magic spell, but there has to be an engine room making it happen.
Oh, there is. Docker relies on a classic client-server architecture. When you, the user, open your terminal and type Docker run or Docker pull, you're interacting with the Docker client. The client is essentially just the messenger.
So the client does not build the containers itself.
No. The client takes your command and translates it into a language called a REST API.
Okay.
A REST API is just a standardized way for computer programs to pass notes to each other over a network. The client passes this note to a hidden background program called the Docker daemon, often referred to as Dockered.
The daemon is the true heavy lifter here. It is like the factory manager listening for instructions.
Precisely. The daemon is the component that actually reaches out to the registry to download images, stacks the layers, builds the read-write scratch pads, manages the network routing, and oversees all the active containers.
And the documentation points out a really neat trick here. The client and the daemon can run on the exact same laptop, which is honestly what most developers do day to day.
Yeah, that's standard.
But because they communicate via that REST API note passing system, you could use a local client on your laptop to control a daemon on a remote server halfway across the world.
Yep. And if we connect this to the bigger picture, this architecture is the exact reason why modern businesses have completely restructured their operations around Docker.
Really?
Yeah, it fundamentally streamlines what the industry calls continuous integration and continuous delivery, or CI/CD.
Okay, let's define CI/CD for everyone. It is basically the automated assembly line for software. A developer writes code, it gets tested automatically, and if it passes, it gets delivered to the customer automatically.
But before Docker, that assembly line was perilous. A developer would write code on their laptop. It would pass the tests on a specific testing server, but when they pushed the code to the live production server, the whole site would crash.
Let me guess, because the production server had a slightly older version of a system library.
Exactly.
The custom furniture didn't fit in the living room.
You got it. With Docker, the developer writes code inside a container on their laptop. They push that exact same container image to the testing environment. Automated tests run against it. And if it passes, they push that exact same tested, proven image directly to the production environment.
There is zero anxiety about the production server's configuration because the container basically is the configuration. The environment travels with the code.
And because of that, the delay between writing code and safely putting it in front of customers drops from weeks down to literally minutes. Fast, consistent delivery.
And beyond delivery, the other massive business value highlighted in the text is responsive deployment and scaling.
Yeah, because containers share the host kernel and skip the heavy boot-up process of a virtual machine, they start incredibly fast.
Right.
If an e-commerce website suddenly goes viral on social media and traffic spikes 1,000%, the server infrastructure has to react immediately.
And if they were using traditional virtual machines, they would have to wait several minutes for new operating systems to boot up just to handle the traffic.
Yeah, and by the time the VMs are ready, the customers have already experienced a crashed website and left.
But with containers, the system can dynamically scale up, spinning up 50 identical lunchboxes in a fraction of a second to absorb the traffic spike.
Exactly. And when the viral moment passes and traffic dies down, the system tears those containers down instantly. So the company isn't paying for heavy server capacity they no longer need.
To bring this entirely out of the abstract, the What is a Container guide actually walked the user through a hands-on example that perfectly illustrates this magic.
Oh yeah, the desktop example.
Yeah. They suggest using Docker Desktop, which is a very user-friendly application that bundles the client, the daemon, and a graphical interface all together on your computer.
And what is the specific example they use there?
So they ask you to search the registry for a pre-built image called Welcome to Docker. You just click Pull to download the layers. Then you click Run. It asks you to map it to host port 8080.
Okay.
And within seconds, you open your normal web browser, type in localhost.a0a0, and you are suddenly looking at a live, functioning website served by a web server.
And we should probably clarify what localhost 8080 actually means. Think of your computer as a large office building, and courts are just the numbered doors on the outside.
Makes sense.
Port 8080 is just a specific door. Docker acts as the bouncer, taking any traffic that comes to door 8080 and routing it directly into the isolated container.
And the absolute brilliance of this exercise is realizing what you did not have to do.
Right.
You did not have to download Apache or Nginx web server software. You did not have to configure routing tables. You did not have to install any underlying infrastructure on your laptop.
You literally just opened a doorway into an isolated world, and that world served you a website.
And the moment I click stop, that entire web server vanishes. It leaves my laptop completely untouched, clean, and totally free of leftover files.
It really is a profound paradigm shift for anyone who works with technology.
So, tying this entire journey together, we started with the chaos of dependency hell, the sheer terror of realizing your code only works on your specific machine. And we saw how Docker solves this by treating applications like self-contained lunchboxes entirely separated from the host infrastructure.
Right, and we learned that by leveraging Linux namespaces to act as blinders, containers can share the host operating system's kernel, making them infinitely lighter and faster than traditional virtual machines.
We looked at the blueprints, the Docker file instructions that stack transparent read-only layers to create an image, and how the daemon adds a temporary read-write scratchpad on top when the container actually runs.
And we saw how this client daemon architecture powers the modern CI/CD assembly line, allowing teams to instantly scale their infrastructure to meet demand without ever fearing environment conflicts.
Exactly. So whether you are a curious learner who wants to experiment with a complex piece of software without polluting your computer's hard drive, or you are prepping to manage a globally scaled cloud application, Docker is the ultimate tool for doing significantly more with far fewer resources.
But before we wrap up, there is one specific detail tucked into the documentation that I think leaves us with a truly provocative thought regarding the future of cybersecurity.
Oh, I love good security implication. What did you find?
Well, the text explicitly states, when a container is removed, any changes to its state that aren't stored in persistent storage disappear.
Right, so that read-write scratchpad layer we talked about earlier just vanishes into the ether.
Yes. Think about the implications of that for system resilience. Historically, if a malicious actor broke into a server and altered a system file, or if a critical bug corrupted a configuration.
It was a forensic nightmare. IT teams had to quarantine the machine, hunt down the altered files, and painstakingly attempt to clean the operating system.
Or, honestly, just throw the server in the trash and spend 2 days completely rebuilding it.
Right.
But with containers, the underlying image is a locked read-only template, and all the changes happen on that temporary scratchpad. So if a container starts acting strangely or an intrusion is detected, you do not even attempt to fix it.
You just terminate it.
Exactly. You instantly delete the container. And in a matter of milliseconds, you command the daemon to spin up a pristine, perfectly unhacked clone from the original locked image.
Wow.
It completely shifts the security mindset from protecting and fixing a fragile machine to instantly replacing immutable infrastructure.
That is incredibly powerful. And it brings us completely full circle to our opening thought. You aren't just building a custom piece of furniture and crossing your fingers that the living room doesn't ruin it. You have essentially figured out how to instantly manifest your perfect garage with your perfect furniture inside it anywhere in the world at any time.
Beautifully said.
And if that garage ever gets a scratch on the paint, you just snap your fingers, the room disappears, and a flawless replica appears in its place in half a second.
That is the magic of Docker.
What a brilliant place to leave it. Thank you so much for joining us on this deep dive. Go out there, pull an image, spin up a container, and see the architecture for yourself. Until next time.